Hi, folks. Um, going to go ahead and move into the next concept. I'm going to split this up into two videos because I don't know how long each one of them is going to take. So surely these will be pretty quick. Let's get right to it. So we talked about history of the atom part in the last video, and now we're going to get into one of the big idea concepts of the modern physics unit that we'll be working with for the next probably 2 to 3 days at least. All right, so starting off here, radiant heat, which I know that brings back fond memories of all the radiometry and luminosity and everything else that we talked about earlier, but we're not going to really be getting into all of that. But remember, radiant means all regions of the spectrum, not just the visible. Okay, so thermal radiation or radiant heat transfer thermal energy by the emission and absorption of photons of light. All right, so we are switching gears a little bit here. Notice I used the term photon. So now we're talking about particle nature. All right, and we'll get more in detail of that here coming up. But basically, anything above absolute zero is going to emit some type of radiation. All right, we should know by now. You know, you take a cast iron skillet and you put it on a burner or stick it over a fire, and it begins to glow red when you get it hot enough. So hence the term red hot. But if we really get it hot, we can get it into the yellow region of the spectrum or even into the violet region of the spectrum if we can get it up high enough. So temperature is directly associated with the wavelength of light that is emitted. Now, as we'll see here, it emits multiple regions, but the photon that is emitted, so if I can get a temperature up to 10,000 Kelvin, the photon that is most likely to be emitted is going to be in the blue end of the spectrum. Okay, so our eyes overall perceive it as being blue hot. Okay, all right. So let's get to our next dead person here that we need to add to our agenda, Max Planck. So Planck was studying a lot of different things, and one of the things they were trying to figure out at the time was just how to make a more efficient light bulb. So he was actually worked for one of the companies. I can't remember which one it was, but anyway, he was trying to study how thermal radiation was affected by the thermal radiation emitted was affected by the amount of energy absorbed. Okay, so what he worked with was called a perfect black body. So if you can imagine taking a cylinder, and we all know that, we walk outside on a hot day and you got a car that is painted black next to a car that's painted white, and you put your hand down onto the car after the sun has been shining on it for a while. The one that is painted black is going to be much, much warmer. Okay, so what they tried to do is work with what was called a perfect black body. So basically, it was a sphere with a very, very small hole that was placed into it. It was hollowed out, but it was perfectly painted black. So what they did is then they had radiation that was absorbed by the black body. So when we have a perfect black body, basically it reflects nothing and absorbs everything. Okay, but they can measure through the opening the radiation that is emitted based off of the temperature of the black body. Okay, so you can see here based on the diagram that we have the energy being absorbed and then some of the radiation is emitted. Once again, this radiation emitted is based off of the temperature that the black body exists at. So you add thermal energy to the black body, it gets hotter and hotter and hotter, and it changes the emitted radiation. Okay, so basically they knew this part at the time. However, this is where I'll probably butcher some of the physics here. Someone who knows a little bit more about this would probably cringe at some of the way I'm going to explain this, and that's okay. It's a very challenging topic to understand. Basically, at the time, if you can imagine heating this black body up to different temperatures, and it changes the emitted radiation, changes the color. So as you keep adding thermal energy to it and you get the temperature higher and higher and higher, what was expected was that the energy of the radiation, and ignore the vertical axis of this graph. So this is wavelength plotted on the horizontal axis. So the wavelength keeps decreasing and decreasing, which means higher frequency, so higher energy, as we'll get to here in a second. So as energy was added to the black body, they would get higher frequency ranges that were emitted. But as the energy was continued to be added, what happened was, instead of continuing this graph out and getting to follow the classical theory at the time, where the modes of energy transferred, you would think it would keep increasing the frequency as you add more energy to it. But what happened here in this ultraviolet range, the graph fell off. Okay, and this is what called the ultraviolet catastrophe. Okay, so basically, classical theory at the time was based off of waves. Okay, light behaving as wave, and even just calculations in waveforms was based on classical theory. So basically, the more energy you add, the higher the frequency was going to continue to be. But instead, no matter what they measured, they would get this fall off at near the ultraviolet region of this. Okay, and so basically what Planck said was, in order for this to make sense, instead of treating light as a wave, we need to treat it as discrete units, and we need to quantize those discrete units. So hence, this was kind of the start of quantum theory. And what Planck decided was that, based off of his equations, and we're not going to get into the math on this, but that the energy was directly proportional to the frequency that was emitted. So you add so much energy, and that energy is going to be emitted as a specific frequency of light. Now, based off of Planck's calculations, obviously energy is not equal to the frequency, but is proportional to. His proportionality constant is a very small number, so this is Planck's constant, which is symbolized with an H, is 6.63 to the negative 34th joules second. Okay? All right, so I'm going to go ahead and skip over this graph here, and I just wanted to read through this and talk about it, because this is about the most simplified, best explanation of this that I could find for you guys. So if we're thinking about classical wave theory, it treats all electromagnetic modes as equally likely, because you can add small amounts of energy to any mode and you can get it to continuously build up. So if we have a perfect black body and we add a certain amount of energy to it, we're most likely to get a smaller frequency. If we keep adding more and more and more energy to it, the higher frequencies that we're likely to get. However, once again, as we kept adding energy to this black body, once we got to the violet end of the spectrum, the graph fell off, and that did not satisfy the classical wave theory. So instead, the quantum view that Planck based his theory on is it's all or nothing. Instead of continuously adding little minute amounts of energy and getting a progressively higher and higher frequency, instead, you basically had to treat it as you either get the energy of one photon or you don't get any energy at all. So in order for a photon to be released, you had to have an energy high enough that you could get that particular photon. All modes are just as likely to happen. So hence, on the graph, you can see that even though we end up getting most of it at 5,000 Kelvin, we get most of the photons released in the blue or violet end of the spectrum. We could also get some red photons released. We could get some violet photons released, and so on. But it gets harder and harder and harder to release ultraviolet and radiation beyond that, because of so much energy that would be needed. Okay, since the excitation of a high frequency photon takes an energy very, very high, it's less likely for it to happen. So basically, in a nutshell, instead of continuously being able to add energy and getting higher frequency photons as a result, Basically, it was just the most probable photon that could be emitted from that based off of the amount of energy. So in order to get anything in the ultraviolet range, you're going to have a ton of energy available in order for that photon to be released. Okay, hopefully that made somewhat sense. We will utilize this concept in the next video and talk about Einstein a little bit.